Hello, and welcome to Team 4's video presentation for a multi-purpose pick-and-place robotic arm guided by a real-time embedded vision system. Today's largely human-driven waste management systems are struggling to keep up with the ever-increasing waste output of the world. With Greater Manchester alone generating 1.1 million tons of waste each year, companies are seeking solutions to increase the efficiency of their waste management plants to optimize sorting. Automation is an obvious solution to improve the sorting efficiency of these plants, as well as potentially reducing worker risk. With the advent of machine learning, detection of desirable objects from the waste stream becomes feasible and has broad applications in this space as well as many others. The purpose of the pick-and-place robotic arm is to explore solutions to help tackle the problem of waste management, specifically at the Kenny Waste Management site, who are sponsoring this project. The desired application is on an operational recycling conveyor at the end of their sorting process. To approach this problem, aims have been laid out to create an appropriate solution. Initially, create a useful data set of wooden pieces from the Kenny Waste Management site to train, as these were the chosen desirable objects. Then, pick, tune and train a machine learning model using the acquired data set. Further, incorporate this model into a standalone system capable of detecting sorted materials from the waste stream. This system will then be incorporated with a robotic arm capable of picking the detected object from the waste stream and placing it off to the side. Programs running on the embedded system, as well as the robot control and communication, will be custom made by the group. An extended aim is to be able to categorize the different grades of wood based on their quality. As discussed in these aims, the system is split between computer vision and robotics. This made a clear divide in the two systems to be developed. The vision system fundamentally is a camera connected to an NVIDIA Xavier NX embedded GPU system that runs a trained machine learning model capable of detecting specific objects with high accuracy. In addition to accuracy, the algorithm chosen, YOLO, is particularly powerful for this use case of a moving conveyor belt as it can process images quickly. The robotic system consists of the Nero 1 arm, a 6 degrees of freedom pick-and-place robot with an integrated Raspberry Pi. This Raspberry Pi runs a custom control script capable of interpreting outputs from the vision system and translating them into robotic movements. The two systems talk via a ROS network. The ROS network works wirelessly, communicating through the local area network with the master node running off the Raspberry Pi in the Nero 1. When dividing these systems, effort has been made to offload all hosting and extra processing from the NVIDIA Xavier to maximize the performance of the machine learning model. To supplement the robotic development, simulations were carried out to help learn how to control the Nero 1 arm. These tests were carried out in the RViz simulation suite and allowed for the combination of movements into actions mimicking what would be required for the final system. A second set of simulation tests were done in Copelia Sim, a robot simulation software. This allowed for the use of various robotic arms from hobby-grade ones to industrial scale. Using these different arms, we could compare their real-world performance to the Nero 1 through basic pick-and-place tasks to gauge the kind of improvement the system could achieve with a higher-grade arm. The UR5 robot, as an example, was easily able to pick objects at least twice as fast as the Nero 1. Once the systems were correctly integrated, initial tests were done on stationary objects. These objects included the desired woods, and also featured other objects that might be found in a recycling plant. The system achieved nearly a 100% success rate on picking the wooden pieces from a stationary position. Its main downfall in this scenario was occasional lack of suction from the Nero 1 gripper. Alterations had to be made to the code in order to allow the system to pick objects from the moving belt. This allowed the ARM control script to predict a position down the length of the conveyor based on its speed to intercept the desired object. This had a success rate of around 50% and was largely due to the control of the ARM, as it could not process commands quick enough to enable sufficient suction on the wooden objects. Despite this, the detection performance on the moving belt was still of a high accuracy. However, for the moving belt scenario, it was very clear that a higher grade arm was required to be able to reliably extract objects from a moving surface. The aim of differentiating different grades of wood was not achieved, however it was proved to be possible with a faster processing system. A higher end system than the NVIDIA Xavier could be used to differentiate wood grades quickly enough for the real-time application. Utilizing a higher end robot arm system would also improve the reliability of picking. This could further be improved by the inclusion of a distance sensor, or some way to perceive the height of the object in order to improve the likelihood of a good connection in the Z-axis. We'd like to say a thank you to our supervisors, as well as Kenny Waste Management for sponsoring this project. Thank you for watching.